We take your stack of sources, your research, your core questions, and plunge into the deepest knowledge available. Today, we are doing a deep dive into the invisible infrastructure of modern life. We're talking about the minerals and energy resources that literally build and, well, power our world.
It's the ultimate lesson in ubiquity, really. I mean, if you look around right now, everything from the device you're listening on to the building you're sitting in, it all relies on material extracted from the Earth's crust.
We often just take the physical world for granted, but think about the sheer scale of it. Roads, huge buildings, cars, buses, airplanes, all of it fundamentally relies on minerals. And it goes even deeper than that, doesn't it?
Oh, much deeper. Even the processes that sustain our lives, the function of our very bodies, they all rely on that small but incredibly potent fraction of minerals we consume every day.
And that small fraction is, what, like a catalyst?
Exactly. It's the mechanism that ensures every other nutrient you consume can actually be used by your system. It's the perfect example of how critical structure is to function.
To really drive this home, let's look at something completely mundane, like your toothpaste. When you brush your teeth, you're using a mineral cocktail. You've got silica, limestone, and aluminum oxide. Those are the abrasives, doing the actual cleaning.
Right. And then the fluoride that prevents cavities. That comes from the mineral fluoride.
And what about the look of it?
Well, you can't forget aesthetics. To get that clean, bright whiteness, you need titanium oxide, often derived from minerals like rutile or ilmenite. And if your toothpaste has that little shimmer, that's usually mica, added for sparkle.
So our mission today is to, move beyond the surface. We need to unpack the nature of these essential resources, explore the ancient and surprising ways they're formed, and most importantly, understand why their conservation is just so critical, especially with the demands of our industrial society.
Let's start with the formal definition, because in geology, not everything that looks like a rock is a mineral. Formally, a mineral is a homogeneous, naturally occurring substance with a definable internal structure.
Homogeneous and naturally occurring? That makes sense. But what I find fascinating is just the sheer range of stuff that definition covers.
It's astounding. Minerals range from the hardest substance we know, a diamond, all the way to the softest, which is talc. And this incredible variety all depends on the chemical composition and the precise physical conditions, the temperature and pressure when that structure solidified.
And it's crucial to understand that there are two ways we look at this data, right?
Mm-hmm.
The geologist is focused on the science of it, the formation, the age, the internal composition.
Mm-hmm. But we, as people trying to run economies, we focus on the geography, the distribution, the economics, and the viability of actually getting it out of the ground.
Exactly. We study where it is and how much it costs to get, because that's what ultimately determines if a deposit is even worth pursuing.
Right.
Okay, so let's unpack this classification system, the one used for commercial viability. It goes far beyond just rock or ore. How do we categorize these things?
Commercially, we use three main classes. We start with metallic minerals, which are themselves broken down into ferrous, which contain iron, like manganese and nickel, then non-ferrous, like copper, lead, bauxite, and of course the precious metals, gold, silver, platinum.
Then you have the non-metallic minerals, the often overlooked but indispensable supporting actors like mica, salt, and limestone.
And finally, the energy minerals, coal, petroleum, and natural gas. That classification tells us their primary use. But to really understand supply, you have to look at their mode of occurrence.
Okay, and this is where it gets this is where it gets fascinating. The mode of occurrence determines the feasibility, the ease, and cost of mining. We're talking about how a viable ore is actually created deep underground.
Right. So in igneous and metamorphic rocks, minerals form when molten material or hot gases are forced upward into cracks, crevices, faults, or joints. And as they cool, they solidify. If the occurrence is small, we call it a vein. If it's a large, concentrated mass, it's a lode. This is how we usually find metals like copper, lead, tin, and zinc.
But not all minerals are formed by heat, pushing things up. How does sedimentary rocks fit into this?
Sedimentary formations rely on totally different mechanisms. Things like deposition, accumulation, and concentration in horizontal layers, or strata. Coal is the classic example, right? Formed from compressed plants. But some types of iron ore also form this way. And we also see sedimentary minerals formed purely by evaporation in really arid regions, which leaves behind deposits like gypsum, potash salt, and sodium salt.
And there are even more unique ways they can form. What about the process of just decomposition?
That's a fascinating one. It happens when surface rocks decompose and the soluble materials are dissolved and washed away by water, leaving behind a residual mass of weathered material containing concentrated ores. Bauxite, the main ore for aluminum, is often formed through this exact process.
I always love the sound of placer deposits. They sound like buried pirate treasure.
They are, in a sense. Placer deposits are what we call alluvial deposits, found in valley floors or at the base of hills, formed by gravity and water erosion. The key thing about them is they contain minerals that are specifically not corroded by water. This is why these deposits are famous for precious metals like gold, silver, and platinum, along with things like tin.
And if you look even further, our sources remind us that the ocean floor holds just massive quantities of minerals.
Vast quantities, yes, but often they're too spread out to be economically viable, though we do get common salt, magnesium, and bromine directly from ocean water. The deep ocean beds are loaded with these things called manganese nodules, but getting them up remains a huge, costly challenge.
Before we move on to the massive demand for all this stuff, we have to touch on a crucial point about who owns it. In most places, minerals are nationalized, right? But in certain tribal areas, like parts of Northeast India, resources like coal and iron ore are owned by the local community or even individuals.
And that creates a very complicated legal and ethical situation. For instance, in places like Meghalaya, this led to the practice known as rat hole mining for coal, where family members would dig these long, narrow, and incredibly dangerous tunnels to extract the mineral.
And that practice was later declared illegal, right?
It was declared illegal by the National Green Tribunal, yes. It's a powerful illustration of the inherent tension between communal resource rights, the immediate economic need for local people, and the need for safe, regulated, large-scale extraction. This conflict over who benefits and who takes the risk, it really highlights just how much value is wrapped up in these resources.
And that high value is driven by the sheer volume demanded by our core industries, which brings us to the industrial backbone, ferrous minerals. Ferrous minerals account for roughly 3/4 of the total value of all metallic mineral production globally.
And iron ore is truly the basic mineral. It is the non-negotiable backbone of industrial development. We primarily deal with two types. Magnetite is the finest quality, with up to 70% iron content. It's got excellent magnetic qualities, making it invaluable for specialized things like the electrical industry.
But the industry favorite, in terms of sheer quantity used for steel production, is hematite. And that usually clocks in around 50 to 60% iron. Why does industry so often prefer the lower quality ore?
That's a great question, and it really illustrates the geography of extraction. Abundance often trumps quality. Hematite is generally more widespread and, well, easier to access in large quantities than magnetite, so the overall process is cheaper and more scalable, even with the lower iron concentration.
Focusing on some key logistical innovations, the sources highlight examples like the Belladilla Range, which exports super high-grade hematite. But I'm really struck by the Kudremukh deposits in Karnataka.
Oh, the Kudremukh project is a brilliant case study in engineering. It's a 100% export unit, and the resource is just vast. But instead of the high cost and environmental impact of hauling ore by truck, they transport the processed ore as a slurry. It's a mix of ore and water through a specialized pipeline right to the port near Mangaluru. That technology drastically cuts down on logistical costs and, improves the economic viability.
Another ferrous powerhouse is manganese. You need it for steel, but what's the ratio that makes it so indispensable?
The ratio is incredible. You need nearly 10 kilograms of manganese to manufacture just 1 ton of finished steel. It's a foundational component for the alloy. Beyond steel, it's used in bleaching powder, paints, and even insecticides.
Okay, so let's shift gears to the non-ferrous minerals. These are critical for our engineering and electrical industries, even though we often have deficient reserves globally, making supply a real strategic concern.
And copper is the classic here. It's malleable, ductile, and an exceptional electrical conductor. Its use in electrical cables, electronics, chemical industries, it's just irreplaceable. That's why copper scarcity is such a major industrial bottleneck.
And then we have bauxite, the clay-like substance that gives us aluminum. I love the historical story that's tied to aluminum because it reveals so much about how quickly resource value can change.
The Napoleon III anecdote is just phenomenal. Aluminum was so difficult to refine at first that it was considered a precious metal. Napoleon III reportedly served his most important guests using aluminum utensils, while the lesser guests had to make do with gold and silver.
Wait, really? So aluminum was literally more precious than gold?
It was, for a time, anyway. But then, as refining processes were developed and wider deposits were found, its value just collapsed within about 30 years. It went from the exclusive material of royalty to being a common sight on the streets. And today, its properties lightness, strength, malleability, conductivity make it essential for everything from aerospace to packaging.
Moving on to the non-metallic essentials. Mica is absolutely indispensable for the modern electronic world. Why is it so unique?
Mica is made of these tiny, layered plates that can be split into ultra-thin sheets. I mean, you could stack 1,000 sheets, and they might only be a few centimeters high. Its value is in its electrical properties. It has excellent insulating capabilities and high resistance to voltage.
So for the non-engineer in the room, what does that technical jargon like low power loss factor and dielectric strength actually mean for my phone or my computer?
It means it's the perfect bodyguard for your circuit board. Because it has high dielectric strength, it can withstand massive voltage spikes without breaking down. The low power loss factor means that when electricity flows through a circuit near the mica, very little of that electrical energy is wasted as heat in the insulation itself. It keeps the electricity precisely where it needs to be, safely and efficiently, even in high voltage environments.
That makes perfect sense. And finally, limestone kind of ties all this industry together.
It does. Limestone, which is found in sedimentary rock, is essential for two big reasons. It's the basic raw material for the entire cement industry, and it's a critical agent used in the process of smelting iron ore in a blast furnace. Without limestone, modern construction and steel production just grind to a halt.
So minerals build the foundation, but energy drives the entire process. Let's transition to the fuel sources that power this global demand, starting with the conventional. The backbone.
We classify energy as conventional, which are typically non-renewable fossil fuels like coal and petroleum, but we also include things like hydropower and firewood, and then non-conventional, which are the renewable sources we have to increasingly rely on.
Coal is the most abundantly available fossil fuel. It's formed by the compression of plant material over millions of years, which results in 4 different grades defined by heat, pressure, and time.
Right, you move up the grades. Peat is the lowest high moisture, low carbon. Lignite is a low-grade brown coal, used mostly for electricity generation. Then you hit bituminous, which is the most popular commercial coal. This high-grade coal is what we call metallurgical coal, the stuff required to make steel. And finally, anthracite is the highest quality hard coal. The difference between them dictates whether you can run a steel mill or just, heat a home.
Next is petroleum, which acts as a kind of dual resource. It provides fuel and lubricants, but the refineries also act as a nodal industry for countless other sectors, feeding raw materials into chemicals, plastics, and synthetic textiles.
And petroleum occurrences are usually associated with large geologic structures like anticlines and fault traps in rock formations. Because petroleum is a thick liquid, the lighter natural gas is often found sitting right on top of the oil in these traps.
And natural gas is rapidly becoming a preferred source.
Absolutely. It's now the preferred transport fuel CNG and cooking fuel PNG because it burns cleaner. But its expansion relies heavily on infrastructure. The massive Hazira-Vijaypur-Jagdishpur, or HVJ, cross-country gas pipeline was like an artery that dramatically expanded the gas grid, making the resource available nationwide.
And conventional electricity is generated either by hydro, which is renewable, like the Bakro Nangal project, or thermal, which uses non-renewable fossil fuels. Now, given the indispensable benefits of these resources, we have to talk about the true, heavy cost of their extraction.
This is a sobering part of the deep dive. Mining is often called a killer industry. Miners are constantly vulnerable to severe pulmonary diseases, silicosis, for example, from inhaling all that dust and noxious fumes. And safety is a daily threat, from collapsing mine roofs to inundation from water and underground fires.
And the environmental consequences are just widespread and often irreversible.
Yes. The land and soil are fundamentally degraded by dumping massive amounts of waste and slurry. Water sources get contaminated by the chemicals used in processing and the runoff from the mine itself. And the constant dust pollutes the air far beyond the mine site. When we talk about the low cost of a mineral, we often fail to calculate the true cost to human health and the local environment.
So what does our source material tell us about conservation in light of these immense costs?
It delivers a stark reality check. Mineral deposits are a minute fraction, about 1% of the Earth's crust. They are finite. Geological formation takes millions of years, while our consumption is nearly instantaneous. We're extracting resources that simply will not replenish on any human timescale.
And the problem just compounds itself economically, doesn't it?
Precisely. Continued extraction forces us to mine deeper, which increases the cost of energy and labor, and often you get lower quality ore. This economic trap means we have to shift our strategy away from just raw extraction.
So, the sustainable path forward relies on promoting conservation and aggressively increasing renewable sources. What are the key conservation strategies outlined?
The focus is on the three R's, but technologically applied. First, improving technologies to efficiently use lower-grade ores at lower cost, maximizing what we already pull out. Second, a massive scaling up of the recycling of metals and the use of scrap metal. And third, aggressively finding substitutes, using fiber optics instead of copper, for example, or specialized plastics instead of certain metals.
That brings us to the necessity of non-conventional energy. The rising prices, the geopolitical risk of shortages, and the serious environmental problems caused by fossil fuels make this shift urgent. Fortunately, this planet and places like India are blessed with massive renewable potential.
We can start with nuclear or atomic energy. This is obtained by altering the structure of atoms, which releases immense heat for electricity. The primary fuels are uranium and its resource base, thorium, which is richly found in the monazite sands of Kerala. It's a powerful option that bypasses fossil fuel consumption.
Next, solar energy. India, being a tropical country, has phenomenal potential here. Photovoltaic technology converts sunlight directly into electricity. This is crucial because establishing localized solar generation minimizes rural dependence on burning firewood and dried animal waste.
That dual benefit is so important. By not burning dung cakes and firewood for cooking, you are simultaneously creating energy and preserving valuable manure for agricultural use, which improves soil health.
Wind power is another major player. We see large wind farm clusters emerging, like the massive complex running from Nagarcoil to Madurai. It's a high-return source once the initial infrastructure is in place.
Then there's biogas, which is commonly known as gobar gas in rural areas. It uses the decomposition of organic matter, animal, farm, and human waste to yield a gas with high thermal efficiency.
And biogas provides these critical twin benefits to the farmer: energy security and vastly improved quality of manure. It makes it one of the most efficient uses of biological waste.
We also look to the oceans for tidal energy. This requires building floodgate dams across inlets. As the tide rushes in and out, the trapped water is forced back through turbines to generate power. Optimal sites are found in places like the Gulf of Kumhat and the Gangetic Delta.
And finally, geothermal energy. This uses the heat trapped inside the Earth's interior. To the listener, what is the geothermal gradient and why is it important for power generation?
The geothermal gradient is simply how quickly the temperature increases as you go deeper into the Earth. In specific areas, this gradient is very high, meaning the heat is much closer to the surface. Groundwater absorbs this heat, turns to steam, and that can then be harnessed to drive turbines. We have experimental projects in the high gradient zones of the Parvati Valley and the Puga Valley.
This incredible variety of options really underscores the goal we started with: using resources smartly. Our sources noted that despite all this potential globally, we are still incredibly energy inefficient. The core principle holds true. Energy saved is energy produced.
And if we connect this to the bigger picture for you, the push toward renewables and conservation isn't just about clean energy. It's about fundamentally decoupling development from the relentless, costly, and dangerous extraction of finite resources. When copper is replaced by fiber optics or steel by advanced aluminum composites, the entire global resource map shifts.
We've seen how iron is the indispensable industrial backbone and why high-voltage electronics rely on the unique properties of mica. We've seen the human cost of extraction and the necessity of finding these renewable pathways.
This raises an important question for you to consider. Given our high dependence on basic minerals like iron and the limited supply of crucial conductors like copper, how might the necessary shift towards aggressive recycling and the use of substitutes fundamentally alter the geography of industrial power in the next century? Will economic power move away from extraction sites and toward recycling and advanced processing hubs?
That's a fascinating pivot point for the global economy.
And finally, a provocative thought, building on that Napoleon III aluminum story. If aluminum went from being a precious metal used by royalty to being common with beggars in 30 years, what mineral commodity today that you see in your phone or your car might experience a similar sudden collapse or explosion in perceived value due to technological substitution or depletion in your lifetime?
Something to mull over until our next deep dive. We hope you feel thoroughly well informed.